In this quiz, we're investigating solubility of ionic compounds, and this is a topic that is relevant in the early parts of chemistry where we discuss things as being either soluble or insoluble, and now we're learning some additional layers and how it relates to equilibrium for insoluble compounds. And we're looking at first this table, and we want to know which of these three different ionic compounds is going to be the most soluble. And it may seem strange that it's not found for the silver nitrate, but this simply indicates that it has the greatest solubility. It contains a nitrate, and that means that it is always going to be soluble. Remember, we had this general rule, NCAA number 1, which indicates that if the compound should contain nitrate, chlorate, ammonium acetate, or number 1, a group 1 metal, it will always be soluble. KSP indicates the solubility equilibrium, which is for insoluble ionic compounds, and this shows that for something that's insoluble, we actually do have a very small amount of dissociation, or a small amount of dissociation, I should say, relatively speaking. But for something like silver nitrate that's simply soluble, we know that it effectively goes to completion when it dissociates. It has the greatest solubility. The next question is, of the other two, which one has the greater molar solubility? And these both have KSPs and are going to be insoluble. So here we need to make a calculation, right? The molar solubility is not the same thing as KSP. KSP is an equilibrium constant that will help us calculate the molar solubility. And so let's focus first on the silver chloride. This is our reaction. Solid silver chloride dissociating will form one silver ion and one chloride ion. And the KSP is going to be, therefore, silver ion times chloride ion, the concentrations of each. For this, we do need to set up an ice table, and I recommend we set it up in the following way. Initially, let's say that we are putting in an amount that is going to dissolve, the maximum amount that is going to dissolve. We'll call that S. We'll start with that amount of silver chloride, no silver, no chloride. Well, S is going to dissociate, right? This is the molar solubility. This is the amount that dissociates in water. And when that amount of the solid dissociates, we form the S amount of the silver plus and S amount of the chloride. And so those two are going to form. Equilibrium is just I plus C, initial plus change. And what's going to happen when the molar solubility is put into solution is that we'll have S amount of silver and chloride, and this we can use with KSP. All cells within these ice tables and all for this video are going to be in molarity. Once we have the equilibrium row, we simply plug in. KSP we get from the table. S and S we get from our equilibrium row here, which evaluates to S squared. And taking the square root, we get that the molar solubility for silver chloride is 1.27 times 10 to the negative 5. And remember that solubility, the molar solubility, is not the same as KSP. KSP can calculate the molar solubility, or knowing the molar solubility, we could get KSP. We're going to fundamentally do the same thing for the silver carbonate, but note that the stoichiometry is different, as when silver carbonate dissociates, we get two silvers in a single carbonate. This is our KSP. It's also changed because of that two silvers. We have the silver squared in the KSP expression. Same setup with the ice table though, but note that because we make two silvers, that affects the change row for the silver ions and therefore the amount that's going to be present at equilibrium. And this is what we were talking about in regards to the stoichiometry of this ionic compound. Still though, if we do this appropriately, we go ahead and plug in and we can evaluate that S is equal to 1.26 times 10 to the negative 4, which is a different molar solubility compared to the silver chloride. And what we conclude here is that's actually greater. It's 10 times greater. 10 times as much silver carbonate can go into solution as silver chloride. And note that even though silver carbonate has a smaller KSP, it has the greater molar solubility S and is more soluble. The lesson is that if we want to calculate molar solubility for different salts, like salts with different stoichiometry, we do need to go through a calculation. We cannot just compare KSP. Okay, now what about for silver chloride in a 0.15 molar solution of silver nitrate? And note here that from before, we have the following equilibrium, right? And in this case, we've introduced silver nitrate. Silver nitrate dissociates completely, but when it does so, it makes silver ions. And so when we're trying to put silver into silver nitrate solution, silver chloride into silver nitrate solution, there's already silver present. Some of the spots that the silver ion we're going to occupy are already filled by the fact that this solution has silver nitrate in it already. So that should inform what we would expect qualitatively. Quantitatively, let's set it up pretty much the same way. Let's still put in the molar solubility. This is not in pure water now, but in the 0.15 molar solution of silver nitrate, and be sure that we're applying our initial condition, which is that the silver plus is 0.15 molar. Still, S will dissociate, forming S silver and S chloride, and we'll get the following in our equilibrium row. And given that, again, this is a small KSP value, let's go ahead and try this approximation that the amount of silver ion that's going to be added to this 0.15 molar is negligible, and therefore we can approximate this as 0.15. This simplifies our calculation quite a bit. We put in the following, and we get that the solubility is equal to 1.07 times 10 to the negative 9 molar, which is quite small, certainly not enough to affect the 0.15 molar silver nitrate solution mathematically, and we have also shown that it is much smaller than what we see for the solubility in pure water. That makes sense, as some of the space in solution is already occupied by the nitrate. Finally, we're looking at 4.17 milligrams of silver chloride into a sample of water, and we have a claim that this is a saturated solution as the exact amount was used. No solid remains, and this is a good indicator that it's saturated if solid remains in solution, because you're putting in solid, you're stirring it, you're trying to make as much dissociate as possible, and the fact that you can't get any more to dissociate shows that perhaps the solution is filled, it's saturated. But the question here is, maybe this the exact right amount was used and there just happens to be none left. Is it saturated? And I think there's a few ways to go about this. But first, we definitely need to get the molarity, right? From 4.17 milligrams of silver chloride in this sample of water, we get that the silver chloride concentration is going to be 1.02 times 10 to the negative 5 molar. And right away, we can kind of say, well, this is less than the solubility that has been shown in part B, so we probably aren't there yet, right? This is most likely unsaturated, as we have not added up to the molar solubility. But traditionally, when we look at this, we can often check with Q versus K as well. So would that work too? Note that for this solution, the silver plus is 1.02 times 10 to the negative 5, as is the chloride. And if we calculate Q here, we end up getting 1.6 times 10 to the negative 11 molar, which is less than KSP as shown in the table above, and would also indicate a solution that is unsaturated.